last time, we've got only one example. Today, we are going to solve 3 examples. So here is example 1, and here is example 2, and here is example 3. So we're going to start with that one here. So it's required for the beam shown below to draw the shear force diagram and the bending moment diagram. Here we have a ruler, and here we have a pin, and we have a rectangular distributed loading, and the span of the beam is 6 meters. In order to draw the shear force diagram and the bending moment diagram, the first step need to be done. We need to determine the support reactions. And in order to determine the support reaction, we need to draw the free body diagram. So in order to draw the free body diagram, we are going to replace the supports with reaction. Here we have ruler support. Then we are going to have reaction in y-axis. We are going to call it AY. Here we have pin support. We are going to replace it with reaction in X. We are going to call it BX, and reaction in Y, we are going to call it BY. So when we draw the free body diagram, we are going to have this here. Here we have AY, here we have BY, and here we have BX. Then we need also to get the equivalent for the rectangular distributed loading. Here we have rectangular distributed loading. We need to get, we need to convert it to a single resultant force. And in order to do that, we need to multiply by the area under the diagram. The resultant force is going to be 20 times 6, which is 120 Newton. Now I'm in position in order to use the equations of equilibrium. And we can start with the summation of the forces in x-axis. Here we have only bx, which means that bx is going to be 0. Then we can use the summation of the forces in y-axis. But like you can see here, I have ay and by, and it cannot be solved. Then it's better to use the third equation, which is the moment about any point should equal 0. Then I'm going to end up with 2 options, either to take the moment about A or take the moment about B. If you are going to take the moment about A, you are going to solve BY. If you are going to get the moment about B, then you are going to solve AY. So here we are going to take the moment about B, which means that we are targeting AY. If I'm going to take the moment here, this one is not going to cause a moment. This one is not going to cause a moment. Only AY and 120. AY is going to be clockwise, and it's going to be multiplied by 6 meters, while 120, if you draw the line of action here, is going to be multiplied by 3, and it's going to be a positive moment since it's counterclockwise. So this one is positive, 120 times 3, and AY is negative, is going to cause negative moment. Is going to be multiplied by 6, which is the perpendicular distance. Then you have one equation, one unknown. Easily you can solve for AY. If you are going to solve for AY, AY will be 60 kilonewtons. So now I know the reaction here. I'm in position to use the summation of the forces in y-axis. If I'm going to apply that equation, AY is positive according to the sign convention. BY is positive as well, while 120 newtons is negative. So I already know AY, which is 60. Then I will be able to know BY is going to be 120 minus 60, which is 60 kilonewtons. So now I know BX, I know AY, and I know BY. So now I know all the support reactions. Then I'm going to move to the second step. In second step, we need to know the shear and the moment functions. In order to do that, we need to use the method of section. We need to cut at a random distance x. And in order to do that, we need to know the points of discontinuity. So here, we don't have any point of discontinuity because we don't have a concentrated force, we don't have couple moment, and the distributed loading is not going to change. So here, we are going to get only one section. It could be here and it could be here. It doesn't really matter since the distance is going to be x. So if you are going to cut here, then you are going to have at a distance x. Distance x, the range of the distance is going to be from 0 to 6 meters. And if you are going to cut here, we are going to put the v and the m, and we should not forget their positive senses. So if you are going to use the right part, of course, you could also use the left part or the right part. Here we choose the left part. In the left part, the shear is going to be positive down, and the moment, the positive moment is going to be counterclockwise. So do not forget this. And the distance is going to be x. Now we are in position in order to get expression for the m and for the v. So now we need to get expression for the v and expression for the m. In order to get expression for the v, we are going to use the equation of equilibrium. To be specific, we are going to use summation of the forces in y-axis should equal 0. We are going to apply that formula for that region here. So if you are going to look into y-axis, we are going to have 60 newtons and v, and we have the rectangular distributed loading. Like I said before, please do not convert the rectangular distributed loading before you make in the section. Convert it to equivalent single resultant force after you cut your section. Please do not do this. Remember to convert the rectangular distributed loading after you cut your section. So here, in order to use that formula, now I need to convert the rectangular distributed loading into single resultant force. We need to determine the area under the diagram. Here the height is 20 and the base is x. So in order to convert it to a resultant force, I'm going to multiply 20 by x. So I have 20 times x down, I have 60 newtons, and I have v. This one's going to be positive, positive, and negative. So I have 60 newtons, which is here, positive. I have 20 Newton meter multiplied by x. It's going to be down here, which is negative. I have v, which is negative as well. Okay. Then we are going to equate that the formula to 0. We're going to set that formula to 0. And then we can simplify the formula and solving for v. Then v came out to be 60 minus 20x, which means that the value of the shear depends on the distance x. If I know the distance x, then I can determine the value of the shear force. Then, in order to find expression for the moment, I'm going to take the moment at the end of the section, which is here. So I'm going to take the moment about the end of the section. Remember the sign convention here. Any force that causes a moment counterclockwise is going to be positive. Then if I'm going to take the moment here, I'm going to have m, which is positive. I'm going to have 60 Newton times x, which is negative. Here I have the rectangular distributed loading. Again, I need to convert it to a single resultant force by multiply by the base, which is x. Now I have 20 times x, and of course, the location is going to be in the middle of x, which means that the distance here is going to be x over 2, and the distance here also is going to be x over 2. So first, I need to convert it to a single resultant force. Is going to be located exactly at the middle, and then I'm going to multiply by the perpendicular distance in order to know the moment. So the moment here is going to be positive because it's counterclockwise, and the force here 60 is going to be negative because it's going to cause a moment which is clockwise times the x, and here we have 20 first time the base in order to convert it to a single resultant force exactly in the middle. So now in this step, the force is just single resultant force in the middle. Then I need to know the perpendicular distance. The perpendicular distance is going to be x over 2. So I need to multiply it by x over 2 in order to get the moment. And the direction is counterclockwise. Then I'm going to simplify this formula here. I'm going to solve for m, and the m came out to be 60x minus 10x squared. Here we have a quadratic equation. Here we have linear equation, and that is of important when you are going to draw the shear and the bending moment diagram. Again, the value of the moment depends on the x distance. If you know the distance x, you could know the moment. So now we are in position in order to draw the shear and the moment diagram. We are going to draw a line of action for the reaction here. We are going to draw the x-axis represents the distance by meters, and the y-axis we are going to put the values of the shear force. Also, I'm going to draw another x-axis to represent the distance, and the y-axis represent the moment. Here, I'm going to draw the shear force diagram, while here I'm going to draw the bending moment diagram. Then I need to recall the formulas. I have formula for the shear force, and I have the formula for the moment. And luckily, we have only one section for that. And the range for those equation for region A, B, which means that from 0 to 6 meters. So now we need to draw first the shear force diagram. Like you can see here, the formula here is the line equation. And in the line equation, we need to know 2 points. And in order to do that, I'm going to know the points here. At that point, x equal 0. And at that point, x equal 6 meters. So I need to substitute 0 here in that equation. So if you put x equals 0 in that equation, then the value of the shear is going to be 60. So at that point, when x equals 0, the moment is 60 kilonewtons. Then when x equals 6, the value of the shear came out to be minus 60. So if we are going to substitute x here equals 6, the value of the shear came out to be minus 60 newtons. So here I have positive 60 Newton, and here I have negative 60 Newton. Then I'm going to connect a line between positive 60 and negative 60. With that, I'm going to done with the shear force diagram. Here we have a strange phenomenon. Here, as we can see, the value of the shear here is 0. And that is very important point to refer to. When the value of the shear is 0, then the moment is going to be maximum. So at that point here, the value of the moment at that location is going to be maximum. So whenever we have that case, we need to take care of that. We need to know the distance from here to here. So in order to do that, we need to equate that, we need to set that equation to 0, because the value of the moment is 0. We need to know when the value of the shear, when When the value of the shear is 0, we need to know the distance x. In that case, it's easy. You can tell that the distance is going to be 3 because the distance, the span is 6. But sometimes it's not like that. You need to set the equation of the shear to 0. Also, you can differentiate the moment and equate it to 0. It will give you the same thing. So before that, in order to draw the bending moment diagram, again, here we have the equation for the moment. As you can see, the equation here is a quadratic equation. Again, it's mean that we are going to have a curve, not a line. So in this case here, we are going to expect to have a curve, not a line. In equation number 1 here, since the equation is the linear equation, we are going to have a line. In this case, we are going to have a curve because here we have a second order equation, not like this one. Again, I need to know, I need to draw some points. I'm going to start with x equals 0. So when x is 0, the moment is going to be 0. When x is 6 meters, the moment again came out to be 0. So here I have 0 and here I have 0. So like I said here, we are going to have a curve, and at the same time, when the value of the shear is 0 here, the moment is going to be maximum. So that point here, the moment is going to be maximum, and that when x equal 3. So if I'm going to set that formula to 0, so 60 minus 20x equals 0, I'm going to solve for x. I'm going to find out that the value of x is 3 meters. So from here to here is 3 meters. So at 3, the moment is going to be maximum. So I'm going to substitute 3 in that formula to know the value of the moment. If you are going to substitute 3 meters here into x, then the formula came out to be 90 Newton meter. So the value of the moment when x equals 3 is going to be 90. So this point is 0. This point is 90. The maximum value at that point is 0. I'm not going to draw a linear line here and linear line here. Why? Because that equation here is the quadratic equation, second order equation, which means that I'm going to have a curve. So I'm going to draw a curve from here to here, from 0 to 90, and curve from 90 to 0 again, because the value here came out to be 0, and the value here came out to be 0, and the value here came out to be 90. Okay, and very important question. You could say that the equation is the equation for the curve. You have quadratic equation. The curve, it could be like that, concave up like that, or it could be like that. Why did you choose the curve to be like that? In this method, in order to have a trick to know whether the curve is like that or like that, we are going to assume the curve here is line. Is a line. So I'm going to assume here I have a line, which means that I have triangle. So if I'm going to have triangle, at the mid of the triangle here, when x equal 1.5, the value is going to be how much? If this is 90 and this one is 0 and this one is a straight line, that means at the middle of the straight line, the value here is going to be 45. So if it was a linear line, then the value is going to be 45. Now, I have the formula for the curve. If I'm going to substitute x equal 1.5 at the middle here, if the value came out to be more than 45, it means that the curve is like that. If the value came out to be less than 45, it means that the curve is like that. So here's a small trick to tell you whether the curve is going to be like that or like that. Then I'm going to substitute 1.5 into the moment equation. Instead of x, I'm going to put 1.5. and the answer came out to be 67.5 Newton meter, which is more than 45. It's mean that the curve is going to be like that. Okay, it's just a small trick to know how to draw the curve. Okay, so the value here came out to be 67.5, which is more than 45. It's mean the curve it's like that. To solve example 3. So here also it's required to draw the shear and the moment diagrams for the beam shown below. Here we have fixed support at A, and we have concentrated force 6 kilonewtons, and the span of the beam is about 3 meters. So the first step, in order to draw the shear force diagram and the bending moment diagram, we need to determine the support reaction. So in order to determine support reaction, we need to draw the free body diagram, and for that we need to replace the supports by support reactions. So here we have fixed support, which means that we are going to replace it with reaction in X, reaction in Y, and couple moment at A. So we are going to have MA, AX, and AY. Then we are in position in order to apply the equations of the equilibrium. First, we are going to start with summation of the forces in X axis should be 0, and we are going to use the sign convention. We don't have any force in X except for AX. It's mean AX is 0. Then we can apply the summation of the forces in Y axis should equal 0, and we need to take care of the sign convention. According to the sign convention here, AY should be positive and 6 kilonewtons should be negative, and we have only one unknown and one equation, AY equals 6 kilonewtons. Then in order to know MA, I should apply the third equation. We need to take the moment about a point where I can calculate the value of MA. It could be here or it could be there. I'm going to choose a point A here. I'm going to take the moment here. And also we need to take care of the sign convention. So MA is going to be positive, and AX and AY will not going to cause a moment, while 6 kilonewtons is going to be multiplied by distance here, 3, and is going to cause clockwise rotation, which means that the moment is going to be negative. Again, here we have one equation, one unknown. I can easily solve for MA. MA came out to be 18 kilonewton meter. So now I know all the unknowns. The moment came out to be 18 kilonewton meter, and the reaction here, AY, came out to be 6 kilonewtons, and the AX came out to be 0. So now I'm in position in order to get the shear moment functions. So now in order to get shear and the moment function, I need to take sections. And in order to do that, I need to know the points of the discontinuity. Here, I don't have any point of discontinuity. The concentrated force, it's located in the end, so it's not going to affect my point of discontinuity. I don't have couple moment. I don't have distributed loading. So I'm going to end up with only one section. So if I'm going to cut here, here, or here, it will give me the same thing. I'm going to cut at a distance X. So I'm going to have only one section. So here I'm going to cut somewhere here at distance X, and the range of X between 0 and 3, from here to there. I need to put the positive senses, V down, the M counterclockwise, and then I need to determine, or I need to come up with expression for the shear force and the moment diagram. In order to do that, for the shear force, I'm going to use the summation of the forces in y-axis should equal 0. I'm going to use that formula. Here is the sign convention. Then I need to look into the y-axis. I have 6 kilonewtons, and I have V. This one here is going to be positive, while the V is going to be negative. So 6 is positive, and V is negative. Of course, 6 minus V equals 0. That means the value of V is 6 kilonewtons. The value of the shear in the whole region is constant, which is 6 kilonewtons. Then I need also to come up with expression for the moment. For that, I need to take the moment at the end of the section. So I'm going to take the moment at the end of the section. Do not forget about the sign convention. Then the moment is going to be positive, and the moment here is going to be positive as well. And the force 6 kilonewton is going to cause a moment, if this is the point of rotation, is going to be clockwise, which is negative. So I have M positive here. I have 18 kilonewton positive as well, while the 6 kilonewton is going to cause a negative moment by and the perpendicular distance is going to be x. Now I can simplify that formula here in order to have expression for the moment. The moment equals 6x minus 18. Here, the value of the moment, it depends on the value of x. And the range of that equation is from here to there. So now we are in position in order to draw the shear and the moment diagram. I'm going to put the line of action. I'm going to put the x-axis for the distance, y-axis here for the shear force, again x-axis for the distance, and the y-axis for the moment. Then I need to bring back the equations that I have developed in the previous slide. The V equals 6 kilonewtons, and the moment equals 6x minus 18. So now I need to draw the shear force diagram. Here, the value of the shear is 6 kilonewton, which means that the value is constant from here to here through the beam. So I'm going to put a line here, which represents 6 kilonewtons. That one is very easy. Whenever I find the value is constant, drawing a constant is very easy. It's just a straight line. And the value here is 6 kilonewtons. Then I'm going to draw the bending moment diagram. Here I have linear equation. I need to look at the equation, whether it's constant or linear or quadratic equation. This time it's a linear equation, which means that I'm going to draw straight lines. And for that purpose, I need to know 2 points in order to draw the line. So here I need to substitute x when x equals 0 here, and when x equals 3 meters. When x equals 0, if I substitute 0 here, the moment came out to be minus 18 kilonewton meter. When I substitute x equals 3 meters, the moment, if this one is, if x is 3 here, that means the moment will be 0. So when x equals 0, I have minus 18. If it's minus, I'm going to put the point below the x-axis. So minus 18 is going to be here, and here I have 0. Then I'm going to connect this point with that point. So here I have minus 18 kilonewton. Since it's down, it means it's minus value. Okay. Do you have any questions about that problem here? Now we have example 4. So in example 4, again, we have a beam, and we have pin support and roller support. This time we have couple moment at the point C, exactly at the middle of the beam. So we need to develop expression as a function of x, and also we need to draw the shear and the moment diagram. So the first step need to be done. We need to determine the support reactions. And to do that, we need to draw the free body diagram. We are going to replace the supports with support reactions. instead of the pin support, we are going to have reaction in X and reaction in Y. And instead of the ruler support, we are going to have only reaction in Y. So I have AX, I have AY, I have BY. Then I'm in position in order to apply the equations of equilibrium. If I'm going to say that summation of the forces in x-axis should equal 0, I have only AX, and AX should equal 0. Then if I'm going to apply the second equation, which is the summation of the forces in y-axis, I'm going to end up with two unknowns, AY and BY. So I'm going to use the third equation. I'm going to take the moment about a point. And my options are point A or point B. It doesn't really matter. I'm going to take the moment about the point B. So if I'm going to take the moment about the point B, then AY is going to cause a counter-clockwise moment, which is negative, and the perpendicular distance, if I'm going to draw the line of action, the perpendicular distance will be 6 meters. And here I have couple moment, and the direction is clockwise, which is negative as well. So I have minus AY times 6 meters, and I have minus 30 kilonewton meter. And we should set that equation to 0. Then I have only one unknown, which means that the value of AY came out to be minus 5. I assume the direction of AY to be up. But when I solve the problem, the answer came out to be negative, which means that the real direction is down. Then I'm going to use that equation here, the summation of the forces in y-axis should equal 0. Then I'm going to have positive AY plus positive BY. Then the value of AY is minus 5. Since it's minus 5, when I move this one to right-hand side, it's going to be positive, which means that the value of BY came out to be 5. So the direction here is correct. The direction here is incorrect. Then I'm going to draw all the unknowns. So this time, instead of the minus, I'm going to change the direction of the force. So I'm going to put the direction down, but the value is positive. And this one also came to be out like that, no problem with BY. So now I'm in position in order to get expression for the shear force and the bending moment diagram. So now we need to get expression for the shear and the moment function. Again, we need to look at the points of discontinuity. This time we have point of discontinuity, which is the couple moment, which means that I need to get two sections. I'm going to have section here in that region, and I'm going to have another section at that region here. So I'm going to cut here at a distance x, like that, and I'm going to put the V and M with their positive senses, and the range is between 0 and 3. And I need to cut here. I can take the left part or the right part. This time I'm going to take the right part so that you can learn. You can use either the left part or the right part. For me, if I'm going to take the right part, it's going to be easier than taking the left part, because in the left part I'm going to have the couple moment here. So I'm going to take the right part here. So here I'm going to take the right part. Again, do not forget the positive senses is going to be opposite to this one here. And range is going to be from 0 to x. Remember, my x here is going to be 0x is here, and I'm going to move from here to here. By this is going to be easier for me. So in that part, I took the left part, and in that section, I took the right part. So let's start with the first section in the region AC. So in the region AC here, I took that section. I'm going to find expression for the shear force diagram and the moment bending moment diagram. For the shear, I need to use that formula. Summation of the forces in y-axis should equal 0. I have 5. According to sign convention, it's negative. And the V also, it's negative according to the sign convention. So I have minus V minus 5 equals 0. It means the value of V is minus 5 kilonewtons. The value of V is constant, which means that drawing the shear bending diagram is going to be easy for me since the value in that region is constant. Then I need to find expression for the moment, and for that I need to take the moment at the end of the section, which is here. Also take care of the sign convention. That sign convention is very important. So I have the moment is going to be positive here, and 5 kilonewton also is going to cause a positive moment. I multiply 5 kilonewton by x in order to know the moment. So I have positive m and I have positive 5x. I can easily put expression for the m. M came out to be minus 5x. And the moment here, the value of the moment, it depends on the x. Okay, and it's good here. The value is a linear equation, which means that when I'm going to draw the moment, I'm going to have a line, straight line. So now let's move to other section. I cut here. I find expression for the V and the M. Now I cut here. I took the right part. I could have taken the left part, but this time I want to show you how to solve effectively. So I'm going to take the right part for the region BC. So here we have the region BC. We took the right part, and this equation is valid from 0 to 3. Here is going to be x equals 0, and here x equals 3. In order to find expression for the V, I need to use that formula. Summation of the forces in y-axis should equal 0. According to sign convention, this one is positive, and this one is positive as well. So I have V plus 5 equals 0. That means the value of the shear is going to be minus 5 kilonewton, which is constant value. In order to find expression for the moment, I'm going to take the moment at the end of the section, which is here. And do not forget about the sign convention. The value of the moment is going to be negative, and the value of the moment here is going to be positive. I'm going to multiply it by x. So the moment is negative here, m is negative, while the 5 kilonewton, since here is the point of rotation, this one is going to be positive. I'm going to solve for m. M came out to be 5x. Again, the value of the moment here, it depends on the distance x, not like the shear. And it's a good thing here we have a linear equation, which means that we are going to have a line. So now I'm in position in order to draw the shear and the moment diagram. I'm going to put action line here and here and here. I'm going to draw the x-axis to represent the distance, v here to represent the shear force, x here for the distance, and m here for the moment. Here I'm going to draw the shear force diagram, while here I'm going to draw the bending moment diagram. I need to bring the equation for the region AB and for the region BC. So I have equation 1, 2, 3, and 4. This equation is going to be valid only in that region, while those equations are going to be valid only in this region. Okay, x is going to start from here, while x here is going to start from there. Now I need to draw the shear force diagram. In this region, I'm going to look into that equation. It's good. The value of the shear is constant. Minus 5 is going to be down. We say that negative values, we are going to plot it below the x-axis. So here we are going to have 5 kilonewton in this region. And luckily, in that region, the value of the shear also is minus 5. So here I have -5 and -5. I'm going to draw a straight line -5, as easy as you can see. So now I'm done with the shear force diagram. Now I need to draw the moment, bending moment diagram. For this region, I'm going to use that equation 2 here, and the moment is -5x. I need to know the moment at that location and at that location. And at this location, the value of x is 0. So when x is 0, the moment is 0 as well. Also, I need to know the moment when x equal 3. Here we have linear equation, which means that if I know 2 points, then I'll be able to draw the line. Here I have 0 at x, and the moment came out to be 0. And here at x equal 3, the moment came out to be -15. So here I have -15, and here I have 0. So I'm going to connect them. So I have moment -15 kilonewton meter. Now for this region, I'm not going to use that formula because we said that this equation here is only valid for that region. For this region, I need to use that formula. Remember, when we took the section, we started x from here. So x here is 0, and x here is 3 meters. So I need to substitute again 2 points. When x equal 0, that means the moment is going to be 0. When x equal 3, the moment is going to be +15. So I have, when x is 0, here I have moment is 0. When x is 3, the moment is +15. Which means that I'm going to draw a line from here to there. So now I have the bending moment diagram. Like you can see here, the couple moment is going to create a point of discontinuity here. The moment before the couple moment is totally different than the moment after the couple moment. If you remember the first example, we had concentrated force here. The concentrated force here, the shear before the concentrated force is totally different than the shear after the concentrated force. So the coupled moment is going to affect the bending moment diagram, like you can see here. It doesn't have any effect on the shear diagram. You can see here the formula here is the same as here. But regarding the moment, we have 2 equations, we have 2 values. Okay, so whenever you have concentrated force, that is going to change the shear force diagram. It's going to create point of discontinuity. If we are going to have a couple moment, it's going to create a point of discontinuity in the bending moment diagram. The more you solve, the more you become good at it. And by the time you are going to be experienced drawing the shear and the bending moment diagram. You can even draw the bending moment diagram without equations. And we have another method in order to draw the shear and the bending diagram. Here we are going to use the equation. Next time, or maybe in other course, we are going to use different method. So I'm going to stop here at that